Greetings to the SCUDEM organizers and judges. We are Team 1046. My name is Nguyễn Khoa, a sophomore in computer science at VinUniversity.
My name is Lê Thanh Sơn, also a sophomore in computer science at VinUniversity.
And I'm Phát, a junior in computer science at Ho Chi Minh City University of Technology.
And we are chosen to address the problem A titled Sweet Tooth and Heavy Metal. Some chocolate products may contain high level of heavy metals. When people consume these contaminated chocolates, there is a great bioaccumulation of these harmful materials in their body. This means that over time, this metal can build up to a toxic level, potentially leading to serious health effects. Our analysis focused on these three main questions. Each of the questions highlights specific aspects of heavy metal bioaccumulation, considering both the amount consumed and the frequency. Studies indicate that chocolate can contain measurable level of heavy metal, especially lead, cadmium, and nickel. Other metals may be present in small amounts but are generally not significant. Here's a table showing the level of heavy metal in chocolate, particularly in candies.
We assume the intake amount is uniformly distributed, whose value is non-zero in the consumption range. This encourages us to take the addition of two sigmoid functions. Here's an example. The total amount of intake is calculated as the area under the curve, in which we get the integral as described. To maintain normal functionality, a certain amount of heavy metal must be stored in the body, which is the motivation of the equilibrium state. The idea of this function acts as a continuous if function, which eliminates values outside the range. As shown earlier, obviously we can set x as the ratio of the current amount of heavy metal and its baseline amount. Other parameters are explained in the slide.
These are the general assumptions used for both children and adults, with parameters adjusted for each specific cases. These are also general assumptions applied to both cases. Here are the assumptions we make for children. Similarly, there is the adjusted version we set for adults. This is the equation we use to calculate the CD adjustment rate, and this one we use to calculate the nutrition concentration. This equation calculates the CD intake based on the nutrition concentration. This equation helps us control the CD transfer rate from blood to organs, and this is the full version of transfer equation. This diagram shows how cadmium moves through the body. After ingestion, it enters the bloodstream and then transferred to the kidney, liver, lungs, and bones. Each organ processes and eventually excretes cadmium into urine, illustrating cadmium distribution and gradual elimination from the body. This is the differential equation used to calculate the amount of cadmium intake into bloodstream and the equation for the total cadmium accumulation in the body, and this one is used to calculate cadmium accumulation in each organ. All the coefficients will be adjusted to fit specific cases. These two plots show the case of continuous multiple intake over 3 years for children followed by cessation, along with the corresponding analytical insight. These two plots show the case of continuous multiple intakes over 3 years for adults, followed by cessation, along with the corresponding analytical insight. These two plots show the case of children whose birthday is close to the holiday period, followed by cessation, along with the corresponding analytical insight. These two plots show the case of children whose birthday is far away from the holiday period, followed by cessation, along with the corresponding analytical insights. These two plots show the case of children consuming chocolate over a long period after the holiday, followed by cessation, along with the corresponding analytical insights. These two plots show the case of children binging on chocolate during the holiday, followed by cessation, along with the corresponding analytical insights. Due to a very low existence rate, cadmium level in the body take a long time to decrease, leading to nearly continuous accumulation if the intake is frequent. Cadmium level can fluctuate based on the nutrient intake, iron, calcium, zinc, which affect absorption and follow periodic patterns. In our closed system, organ cadmium level can adjust to meet the body needs but still keep the total cadmium accumulation stable over time. Here's a summary of health impacts by cadmium levels. As cadmium level raise, health risks become progressively more severe.
Here we define the baseline lead levels in blood, bones, and soft tissues. Children absorb lead at a much higher rate than adults, making them more vulnerable. Lead distributes between blood, bones, and soft tissues, with bones serving as a long-term reservoir. Lead accumulates mainly in cortical bones with a half-life of 15 years, while trabecular bones have a shorter turnover. The blood and soft tissues clear lead within a month. Calcium intake significantly modulates lead absorption rates. This flowchart illustrates lead transfer dynamics. The rates with F notations are age-dependent. These equations describe lead dynamics across compartments, which model storage, resorption, and excretion. Age-dependent rates are simulated using these sigmoid-like functions. All the rates are then scaled with the correct x-axis to handle the baseline lead levels. The initial lead levels and rate values are calibrated based on known half-lives and physiological behaviors. In this scenario, soft tissues accumulate lead close to the harmful threshold of 5 microgram due to increased absorption and calcium deficiency. With high calcium diets, soft tissue lead levels rise slowly and stay well below harmful thresholds, highlighting calcium's protective effect. Adults show much lower GI absorption rates, resulting in stable and safe soft tissue lead levels. Short recovery intervals between holidays lead to cumulative lead accumulation, with soft tissues nearing harmful thresholds. Blood lead occasionally spikes to dangerous levels due to bone resorption. Longer recovery intervals allow lead in soft tissues and blood to clear, reducing health risk. Bone lead still accumulates gradually due to its long half-life, but blood lead stays well below critical levels. Distributing lead intake over 30 days provides enough time for soft tissues clearance, keeping lead levels manageable. This approach poses no significant long-term risk. Binge consumption leads to immediate and dangerous spikes in blood and soft tissue lead levels. Despite sufficient recovery time between holidays, this highlights the acute risk of binge patterns.
The model operates on baseline assumptions, including initial equilibrium concentrations of nickel in blood, bones, and soft tissues. Nickel absorption rates between 20% to 40% from oral intake to blood, differing between adults and children, as does organ distribution, which is detailed here for clarity. Finding shows that nickel also redistributed from bones to organs, whose percentage is shown here. Nickel initially circulates in the blood, then distributes to organs like the kidneys, liver, and bones. Kidney plays a major role in excretion. Bones continuously redistribute nickel, delaying equilibrium. Since urea merely serves as a pathway for nickel excretion, we can exclude it from the model. Blood distributes nickel to the other organs based on factors like maximum capacity, allowing us to calculate these rates with sigmoid scaling functions that account for nickel intake and storage limitations. We multiply two scaling functions mentioned above, where each transfer rate is scaled. X1 is described as the ratio with the maximum capacity, and X2 is described as the ratio with the minimum capacity, or the equilibrium state. Since iron affects the intake amount of nickel, only transfer rate from oral to blood is scaled using the ratio of iron. Our parameters are set based on the findings of Agency for Toxic Substances and Disease Registry. We assume the minimum capacity be the equilibrium. The distribution of nickel from blood to locations is displayed as below. With the half-life values as previous, we use the formula R equals to ln 2 divided by the half-life in hours to calculate the excretion rate, which results in the following parameters. Here, we model a one-time nickel intake in children, showing how the kidney initially accumulate nickel. The kidneys then excrete it over time, while bones retain it longer. The result for adults is quite similar, where the main amount of nickel is distributed in kidneys. In this scenario, with repeated intakes, nickel builds up primarily in the kidneys, which struggle to excrete it quickly enough. Bones also retain some of this nickel, creating lasting accumulation that doesn't fully clear between doses, leading to a gradual increase over time and health issues. In this scenario, nickel intake is spaced further apart, allowing kidneys to excrete most of it between doses. However, some nickel still accumulates in bones and soft tissues, creating a periodic increase in overall levels with each intake. Distributed intakes. Nickel levels in organs show a stable periodic pattern. The kidneys excrete much of the nickel between intakes, but bones and soft tissues retain some, leading to a gradual accumulation over time. Following a large rapid intake, nickel accumulates heavily in the kidneys, which take longer to process the excess. This leads to prolonged retention, especially in bones and soft tissues, increasing the risk of potential health effects due to slow excretion. Just like previous, but after reaching capacity, nickel slowly builds up in the blood and other areas. Excretion occurs only after a prolonged period.
In conclusion, first, long-term heavy metal accumulation occurs with regular intake exceeding the body's excretion ability, leading to potential organ damage over time. Second, large candy consumption during near holidays increases heavy metal levels due to insufficient time for excretion. Third, spaced-out consumption allows the body to excrete heavy metals between periods, reducing toxicity and long-term health risk compared to binge patterns. Our limitations are lack of real-life data, the assumptions, and limited generalizability. And lastly, our future work would be model refinement, complex system integration, and scalability.